You spot something racing through space at 221,000 kilometers per hour. Object designation, A11PL3Z, July 1st, 2025. The Atlas telescope in Rio Hurtado, Chile catches it. Hyperbolic trajectory, not bound to our sun, moving too fast. This thing came from another star system, the third confirmed interstellar visitor ever. They rename it 3I Atlas. The I stands for interstellar. Number 3, because only 2 others came before. 1I Oumuamua in 2017, 2 I Borisov in 2019. Now this, and nothing about it, follows the script. First clue drops fast. July 2nd, 2025, Nordic Optical Telescope. David Jewett confirms active coma. Dust, gas, outgassing, classic comet behavior. But wait, July 4th through 5th? Hubble space. Telescope images show something strange. A teardrop cocoon facing the sun, no tail behind, just this weird anti-tail pointing sunward for weeks. Gemini South Telescope catches it, August 27th. Now there's a faint tail away from the sun, standard comet stuff. Except the brightest point stays locked on the nucleus. Every single image. That's not normal for active outgassing. If you value documented astronomical anomalies and interstellar object analysis like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. The script is researched and factual, using sources from the Minor Planet Center's 4,022 observational data points, compiled between May 15th and September 23rd, 2025. Analyzed by Richard Klote, Avi Loeb, and Peter Veers at Harvard, published September 24, 2025. Plus James Webb Space Telescope NIR spec observations. From August 6th, published August 25th in Archive Paper 2508.18209 by Martin Cordner's team at NASA Goddard Space Flight Center. Now back to the information. Gran Telescopio Canarias. 10.4 meter mirror, Canary Islands, July 2nd through 5th, 2025. Raul de la Fuente Marcos runs photometric analysis. Light curve shows periodic variation. Low amplitude, 16.79 hours, plus or minus 0.23 hours. That's the rotation period. Confirmed. Published in Astronomy and Astrophysics, August 5th, Paris Personnel, 2025. Independent verification comes from Tony Santana Ross, multiple telescopes, July 2nd through 29th, slightly shorter period, 16.1, 6 hours plus or minus 0.01 hours. Published August 25th. Both studies match. Nucleus spins once every 16 to 17 hours. Why does rotation matter? Objects ejected violently from planetary systems spin fast. Close, passed by a gas giant torques them, kicks them out spinning. Gentle ejections from dying stars, losing mass produce slow rotation. 16 hours sits middle range. Not extreme either way, but combined with everything else, it tells a story. Shape matters too. Steady rotation suggests spherical nucleus. Wobbling rotation indicates elongated form like Oumuamua's cigar or pancake shape. 3. I Atlas rotates steady, regular period, probably not weirdly shaped, just a rotating chunk from somewhere else. August 6th, 2025. Distance from Sun, 3.32 astronomical units. James Webb Space Telescope points its NIR spec instrument at 3I Atlas. Infrared spectroscopy, 0.6 to 5.3 micrometers. Results drop August 25th. Carbon dioxide dominates the coma, not water. Carbon dioxide. The ratio hits 7.6 to 1. CO2 to H2O, 8 parts carbon dioxide to 1 part water. Highest ratio ever recorded in a comet, 4.5 sigma above the trend for long period in Jupiter family comets, excluding outlier C 2016 R2. This thing is chemically bizarre. Martin Cordner at Catholic University of America leads the analysis. His team finds carbon monoxide too, 14 kilograms per second. Carbonyl sulfide, 0.43 kilograms per second. Water vapor, 6.6 kilograms per second. Water ice grains smaller than 1 micrometer. Probably amorphous, not crystalline. But that carbon dioxide emission, 129 kilograms per second, massive. The CO2 coma stretches at least 348,000 kilometers across, based on Spherex observations, August 7th through 15th. Nearly 3 times Earth's diameter just in carbon dioxide gas. Where does that chemistry come from? 3 possibilities. First, formed beyond the CO, 2 ice line and its parent protoplanetary disk. way out where carbon dioxide ice is abundant compared to water. Temperatures cold enough for CO2 to condense solid. Second, radiation cooking, drifting through interstellar space for billions of years. Cosmic rays bombard the surface, create a cooked shell where CO2 ices form. Now the sun heats it, vents that excess carbon dioxide. Third, heat penetration issue, nucleus resists internal heating. CO2 sublimates at lower temperature than water, gets released first. Water stays locked inside, waiting for closer solar approach. Very Large Telescope joins July 20th through August 21st, detects cyanide gas, CN emission, 14.0 grams per second by August 21st, atomic nickel vapor, Ni1 emission, 4.6 grams per second. Rapid, steady increase throughout the observation period. Comet approaches Sun. Distance drops from 4.4 AU to 2.85 AU. Activity ramps up, but here's the twist. No iron. Phi, one vapor not detected. Nickel and iron usually appear together, roughly equal amounts when comets outgas. Not here. Just nickel, no iron. Weird. Explanation? Nickel tetracarbonyl, NiCO4, highly volatile molecule. UV light breaks it apart easily, releases nickel and carbon monoxide. Dust grains in the coma contain this compound. Solar radiation hits it, decomposes. Explains high activity far from sun, explains nickel without iron, industrial chemistry in space, except this formed naturally around some distant star billions of years ago. More strangeness. MDM Observatory and VLT search for dicarbon and tricarbon, C2 and C3 molecules, August 25, not detected. Carbon chain depletion, severe. Luis Salazar Manzano at University of Michigan analyzes the spectrum. 3. iAtlas shows significantly fewer C2 and C3 molecules than any known comet, one of the most carbon chain depleted comets ever measured. The C2 to CN ratio upper limit confirms it, yet the comet glows green. September 7th, 2025. Total lunar eclipse. Gerald Riemann and Michael Yeager photograph 3. iAtlas. Green glow. Clear as day. Published Universe magazine. September 24th. Problem. Green glow in comets comes from dicarbon. C, 2 molecules fluorescing under solar radiation. But 3, iAtlas, has almost no C2. So why green? Either dicarbon exists in unique conditions not yet detected, or some unknown molecule creates the glow. Mystery unsolved. Scientists wait for December close approach to Earth. 1.8 AU. Better observations then. Maybe answers. Carbon isotope ratio. Carbon 12 to carbon 13. JWST measures it. Similar to Earth's ratio. Material created in an environment with similar carbon species to our solar system. Not exotic, just displaced. The nickel emission isn't exotic either, seen in various comets including Tian, Waidiamo, or Borisov. But combined with no iron and high CO2 and carbon depletion, pattern emerges. This comet formed under different conditions than solar system comets. Different stellar environment, different protoplanetary disk, different formation zone. Now the size question, Hubble Space Telescope. July 21st, 2025. Images taken at 277 million miles from Earth. Nucleus diameter constrained, not less than 440 meters, not greater than 5.6 kilometers. Huge range. Why? Coma brightness. Reflective dust around nucleus makes it appear bigger and brighter. Can't separate nucleus light from coma light. Early estimates from July hit 10 to 20 kilometers diameter. Astronomers knew that was too high. Coma contamination. Actual nucleus probably at lower end. Less than 1 kilometer, like Tia Chu, I, Borisov, dust loss rate suggests small nucleus. But wait, September 24th, 2025, new paper, Cloete, Loeb, Veres, minor planet center data, May 15th through September 23rd, 4,022 observations. 227 observatories worldwide. Astrometric analysis, track position against predicted gravitational trajectory, upper limit on residuals, 0.028 arcseconds, over 4.5 months. Translation: non-gravitational acceleration less than 15 meters per day squared. Tiny. Here's the punch. JWST measured mass loss. August 6th, 150 kilograms per second total. Outflow velocity, 440 meters per second. That's rocket effect. Gas jetting from sun-facing side should push the comet. Alter trajectory. Measurable acceleration. But observations show none. Residuals consistent with zero. Pure gravitational motion. Why? Object too massive. Outgassing thrust insufficient to budget. Newton's second law. Force equals mass times acceleration. Same force, no acceleration. Mass must be huge. Calculation: minimum mass, 33 billion tons, 33 times 10 to the 12 kilograms, at solid comet density. Minimum diameter, 5 kilometers. Harvard paper published September 24. Avi Loeb emphasizes the anomaly. 3. I-Atlas, more massive than Oumuamua by 3 to 5 orders of magnitude, more massive than 2I, Borisov, by 3 to 5 orders of magnitude, 1,000 to 100,000 times heavier. Major anomaly. Why anomaly? Interstellar mass budget. Models predict size distribution. Small fragments common. Large bodies rare. Exponential drop-off. Should detect 100,000 objects on 0.1 kilometer scale like Oumuamua before finding 1 5-kilometer scale like 3 Asu die Atlas. But we found only 2 smaller ones. Then this giant doesn't fit expected distribution. Loeb calls it untenable if nucleus diameter exceeds 5 kilometers. Reservoir of rocky interstellar material can't support it. Either model's wrong or something else going on. October 3rd, so as 2025 approaches. Mars Reconnaissance Orbiter Opportunity. High-rise camera, 0.5 meter aperture. 3. I-Atlas passes 29 million kilometers from Mars. Resolution 30 kilometers per pixel. Coma, optically thin, transparent. Central pixel brightness gives strict upper limit on nucleus size. 2 orders of magnitude better than Hubble. Nucleus diameter, answer incoming. If it's bigger than 5 kilometers, models break. If it's smaller, mystery, why so massive remains. Trajectory details, hyperbolic orbit. Eccentricity greater than 6. Inclination 175 degrees. Retrograde tilted 5 degrees from ecliptic. Inbound velocity 58 kilometers per second relative to Sun. Hyperbolic excess velocity, not gravitationally bound, came from interstellar space. Returns to interstellar space. One pass, forever. Heliocentric distance at discovery. 4.5 AU, just inside Jupiter orbit. July 1st, distance when JWST observed, 3.32 AU. August 6th, perihelion, closest to Sun. October 30th, 2025, 1.4 AU, just inside Mars orbit. Planetary encounters. Mars, October 3rd, 0.19 AU, 28 million kilometers. ESA's Mars Express and ExoMars Trace Gas Orbiter ready. High-resolution stereo camera. Color and stereo surface. Imaging system. Omega and SpyCam spectrometers. Nomad spectrometer. All instruments turning toward 3 I-Atlas. Observation campaign. Measure volatile activity. Composition. Spectrum, if bright enough. Venus, November 3rd, 0.65 AU. 97 million kilometers. Earth, December 19th, 1.8 AU. 269 million kilometers. Closest Earth approach. Observing window reopens. Sun no longer blocks view. Jupiter, March 16th, 2026, 0.36 AU. 54 million kilometers. Juno spacecraft nearby. Potential observations. Solar conjunction blocks Earth view. Late September through November. Sun between Earth and comet. Blind period. Coronal mass ejection risk. CME could hit 3 ROS Atlas late September. Tail disruption possible. Trajectory change unlikely. Too massive. But astronomers want to observe CME impact before conjunction. Short window. Limited time. Chemical inventory incomplete. JWST scheduled December observations. Post-perihelion. Peer through coma at nucleus. Direct measurement. Martin Cordner's team hopes for more molecules. Methanol. Formaldehyde. Methane. Ethane. Hydrogen cyanide. Ammonia. Depends what outgasses closer to Sun. Detailed chemical inventory. Compare to solar system comets. Revelatory data. Origin clues. Formation environment signatures. Galactic origin analysis. Raul de la Fuente Marcos runs N-body simulations. Traces trajectory backward. Heliocentric components of galactic velocity. U minus 51.233, V minus 19.456, W plus 18.930. All in kilometers per second. Radiant in Sagittarius. Right ascension 295 degrees. Declination minus 19 degrees. Gaia, DR, 3 data analysis. Statistical sample of kinematic analogs. Result, parent system part of galactic thin disk, solar-like star. Slightly subsolar metallicity, not thick disk, not from ancient halo population. Relatively young stellar neighborhood, similar to Sun's environment. September 2025 study, Yi Yangguo analyzes stellar encounters, past 10 million years. 3. I-Atlas may have passed within 1 parsec of 25 known stars, 3.3 light years. Close approach, gravitational interactions possible, velocity perturbations, trajectory adjustments, parent star unknown, but properties inferred. Metallicity, at least 40% solar, if from thick disk. Formation distance beyond CO2, ice line certain. Chemical composition proves it. Protoplanetary disk chemistry, different from inner solar system. Outer disk formation, cold environment. CO2, dominant. Spacecraft observation network, Hubble monitoring through November. Ultraviolet spectroscopy scheduled. Gas emission composition, sulfur to oxygen ratio. Monitor outbound journey. JWST, December follow-up. NIR spec again, post-perihelion activity. Sphere-X completed August observations. Infrared CO, 2 cloud mapping. Swift Observatory, tentative water vapor detection, July 31st, August 1st. O radicals. Water ice grains sublimating beyond nucleus, 4,000 to 10,000 kilometers from center. Ejected by CO2 and CO outgassing, not water sublimation. Secondary process. TESS observations reveal early activity. Transiting exoplanet survey satellite, May 7th, 2025, 2 months before discovery. Heliocentric distance 6.4 AU, already showing cometary activity. Coma present, active that far out, unusual. Most comets dormant beyond 5 AU, not this one. Carbon dioxide sublimation begins early. Different volatility profile than water-rich comets. Brightness evolution. Mid-July, constellation Sagittarius, apparent magnitude 17.5. Late July, Ophiuchus, magnitude 16. Dense star field, observation challenges, background star confusion. August, crosses Ophiuchus, Scorpius, Libra. September, remains Libra, brightens to magnitude 12 to 13. Peak brightness, expected magnitude 11.5 to 12, never naked eye visible. Requires telescope. 8-inch aperture minimum under dark sky for visual. CCD imaging easier. 150 to 200 millimeter aperture sufficient. Activity level steady through August. No outbursts detected. Smooth brightness curve. Continuous outgassing. No fragmentation events. Contrast 2. I Borisov. That comet fragmented. Lost pieces. Nucleus broke up. 3 I Atlas holds together. Structurally sound. Dense nucleus. Strong material cohesion. Either that or different composition resists thermal stress. Temperature modeling incomplete. Surface temperature at 3.3 AU. Approximately minus 160 Celsius. CO2 sublimation temperature minus 78.5 Celsius at 1 atmosphere. But vacuum conditions different. Sublimation occurs lower pressure. Higher temperature needed. Solar heating sufficient at 3 AU. Water ice sublimation temperature 0 Celsius. Requires closer approach 1 to 2 AU. Perihelion at 1.4 AU. Water sublimation should increase. October observations. Crucial. Dust production rate estimated from coma brightness. AFR parameter measurement, July images. Dust production correlated with heliocentric distance. Power law relationship. Exponent varies. Typical comets, -4 to -2. 3. I Atlas. Data insufficient. Need more observations. Coma size evolution tracked, July 2nd. 26,400 by 24,700 kilometers. Elliptical, Grand Telescopio Canarius measurement, slightly asymmetric, sunward enhancement, typical cometary behavior, radiation pressure in solar wind-shaped coma, teardrop formation, spectral slope analysis, visible wavelength range, 4,000 to 9,000 angstroms, slope S prime equals 18.3% per thousand angstroms, plus or minus 0.9, redder than D-type asteroids, similar to trans-Neptunian objects, similar to centaurs. Comparable to 1 I Oumuamua, redder than 2 I Borisov. Red slope indicates complex organics, carbon compounds, radiation processed materials, interstellar weathering. Cosmic ray exposure creates red coloration, timescale billions of years. Coma, color evolution. July observations, reddish. August observations, redder still. Santana Ross study. Coma became redder throughout July. Evolving composition, surface layers sublimate, expose deeper material, chemical stratification, outer shell different from interior. Radiation processed surface gives way to pristine subsurface, or dust grain properties change. size distribution shifts, composition gradients, albedo estimation uncertain, typical comets, 4% geometric albedo, assumed for 3I Atlas, could be higher, could be lower. Affects size calculation, higher albedo means smaller nucleus for same brightness, lower albedo means larger nucleus, 4% standard assumption, but interstellar object, maybe different. Oumuamua showed unusual reflectance, specular, not diffuse. 3. I Atlas, probably more typical. Dusty coma indicates normal cometary surface, still uncertainty remains. Mass loss sustainability calculation, 150 kilograms per second, multiplied by seconds, days, months, perihelion passage, weeks long, post-perihelion activity continues. December, Earth approach, still active, total mass loss, order millions of kilograms, billions maybe, 33 billion ton nucleus, mass loss negligible fraction, 0.001% at most. Nucleus barely affected, can sustain activity indefinitely at current rate, structurally stable, composition homogeneous throughout, or deep ice reservoirs, non-gravitational forces revisited, 15 meters per day squared upper limit. Compare Oumuamua. That showed 4.9 2 times 10 to the minus 6 meters per second squared. Normalized 1 AU, much larger. 3 orders of magnitude. Oumuamua, tiny, 100 meters scale. Light, easily accelerated. 3I Atlas, massive, 5 kilometer scale, heavy, resistant to rocket forces, physics consistent, F equals ma. Same outgassing force, smaller acceleration, bigger mass, Newton vindicated. But Oumuamua showed no coma, no dust, no gas detection, yet accelerated anomaly there. 3. I Atlas shows classic comet signs. Gas, dust, coma, tail, yet no acceleration. Anomaly here, different anomalies, different objects. Oumuamua tumbling elongated mystery. 3. I Atlas massive CO2 comet, both interstellar, both weird, different weird, radiation pressure effects calculated, solar photons push dust grains, tiny particles affected most, micron size grains, beta parameter, ratio radiation pressure to gravity, small particles high beta, leave nucleus fast, form tail, large particles low beta, stay near nucleus, form coma. 3. I Atlas coma dust, submicron water ice grains confirmed, high beta, should produce prominent tail, yet tail faint until late August, dust production low, grain sizes atypical. Coma opacity confuses measurements. Thermal modeling requires nucleus composition, ice fraction, rock fraction, thermal inertia, thermal conductivity, heat capacity, all unknown. Assumptions needed, pure ice end member, pure rock end member, reality somewhere between. 50-50 mix common assumption. Density 1 to 2 grams per cubic centimeter. Thermal inertia 10 to 100 SI units. Heat penetrates skin depth. Diurnal layer, meters to tens of meters, seasonal layer, deeper. 3. I Atlas rotation, 16 hours. Diurnal cycle. Subsurface temperature lags surface, phase delay, affects outgassing timing, sunward coma enhancement observed, consistent models, dust to gas ratio unknown, typical comets 0.1 to 10, wide range, depends composition, depends heliocentric distance. 3. I Atlas dust component visible, gas component measured, JWST, both present. Ratio calculation requires absolute measurements, dust mass production, gas mass production, data insufficient, future observations needed. AFR gives dust, NIRSPEC gives gas, combine, calculate ratio. Compare solar system comets, impact hazard assessment completed, CNEOS trajectory analysis, NASA Center for Near Earth Object Studies, minimum orbit intersection distance, MOID, Earth MOID 1.8 AU, safe. Venus MOID 0.65 AU, safe. Mars MOID 0.19 AU, close but safe. No collision scenarios. Hyperbolic trajectory. Enters solar system, swings past sun, exits solar system, never returns. One-time visitor. Planetary Defense Office, monitoring concluded. No threat confirmed. Public interest high. 3rd interstellar object. Rare event. Media coverage extensive. Amateur astronomers observing. Chris Shore, photographed from Payson, Arizona. July 4th. Gianluca Massi Virtual Telescope Project. July 3rd. Images worldwide. Gerald Riemann, Michael Yeager, lunar eclipse observation. September 7th. Citizen science contribution, data archiving, historical record, Avi-Loeb speculation, extraterrestrial spacecraft hypothesis, paper posted RCIV, July 16th. Co-authors analyze trajectory, suggest technological origin possible, table of considerations, anomalous characteristics, large size, unusual chemistry, trajectory aligned with ecliptic, within 5 degrees, convenient for solar system exploration, Oberth maneuver potential, reverse propulsion at perihelion, break into solar system, remain bound, speculation controversial. Chris Lintott, immediate criticism. Live Science quotes overwhelming consensus, natural comet, scientists disappointed, distracts from other research. Scott Manley points out statistical flaws. David Kipping criticizes trajectory analysis. Daryl Seligman emphasizes classical cometary activity signatures. JWST confirmed outgassing. CO2, water. CO, natural comet behavior. Spacecraft hypothesis unsupported. Loeb maintains openness. Hypothesis worth pursuing. Test and reject or accept. Scientific method. Dark forest hypothesis mentioned. Fermi paradox resolution. Malign intelligence scenario. If spacecraft. Intentions unknown. Benign or malign. December approach. Potential intercept date. November 21st to December 5th. Testable prediction. Non-gravitational acceleration toward Earth. Evidence of maneuvering. Jupiter intercept alternative. 5.9 times 10 to the minus 5 AU per day squared. Normalized 1 AU. Target rendezvous, March 2026. Also testable. Observations will decide. But mainstream astronomy unified. Natural comet. Interstellar origin. Ejected from exoplanetary system. Billions of years drift. Arrived our solar system. Chemical composition unusual. Size possibly large. But natural. Physics consistent. Chemistry explained. Radiation processing. Formation environment. Ice line distance. All natural processes. Spacecraft hypothesis, extreme, extraordinary claims require extraordinary evidence. Current evidence supports a comet, no spacecraft indicators, outgassing, rotation, spectral features, all consistent natural comet. Formation scenario most likely, protoplanetary disk around sun-like star, galactic thin disk location, metallicity slightly subsolar, planet formation ongoing, giant planets migrate, gravitational scattering, comets ejected. 3 Aurea. I Atlas among them. Outer disk origin. Beyond CO2 ice line. 3 to 5 AU from parent star. Cold region. CO2 rich ices. Water ices present, but CO2 dominant. Carbon monoxide abundant. Organics form. Radiation processing begins. Star evolves. Millions of years. Object drifts away. Enters interstellar medium. Interstellar journey. Billions of years possibly. Age uncertain. Galactic orbit. Velocity. Relative local standard rest, minus 7.2 kilometers per second. Thin disk kinematics, U velocity, minus 51. Perpendicular to galactic plane motion, 18. Radial toward galactic center, minus 19. Typical thin disk star motion. Parent system age, 1 to 10 billion years. 3. I Atlas formation, epoch matching. Ancient object. Witnessed stellar evolution. Parent star possibly red giant now, or white dwarf, or still main sequence. Unknown. Lost in galactic census. Cosmic ray exposure calculations needed. Radiation dose over time. Surface erosion rate. Mantle thickness removed. Pristine interior depth. Current sublimation exposes what layer? Pre-erosion surface, radiation cooked mantle, or pristine core. Chemical gradients indicate outer layers, carbon depleted. C2, C3 gone. Inner layers may be rich. October activity increase tests this. More volatiles released. Chemical inventory expands. Depth layers accessed. Stratification revealed. December approach delivers answers. 1.8 AU from Earth. Best observation geometry. Sun-Earth, comet alignment favorable. Phase angle small. Full illumination. Brightness maximized. Northern hemisphere observers. Southern hemisphere 2. Constellation position. Probably Aquarius or Pisces. Evening sky. Dark sight required. Magnitude 11 to 12. CCD photometry. Spectroscopy feasible. Large amateur scopes. Professional telescopes too. Coordinated campaign. Multi-wavelength. Radio observations possible. Molecular emissions. Radar maybe. Distance marginal. Goldstone. Arecibo gone. Remaining assets limited. X-ray observations attempted. Chandra. XMM Newton. High energy emission. Solar wind charge. Exchange. Cometary X-rays. Faint but detectable. 3. I Atlas active. Coma extensive. Good target. X-ray spectrum, ionization state, solar wind interaction, magnetic field draping, bow shock formation, cometary magnetosphere, induced field, plasma dynamics, all observable X-ray band, outbound trajectory post-perihelion, velocity increases, gravitational acceleration near Sun, slingshot effect, exit velocity relative Sun, 58 kilometers per second, plus perihelion boost, final hyperbolic excess velocity, 60 to 65 kilometers per second estimate, direction outbound, roughly opposite inbound, but perturbed, planetary encounters, Jupiter flyby march, trajectory bent, exit vector altered, galactic velocity components change, new UVW values, different from inbound. Gravitational slingshots work both ways. Final observations. Window, March to June 2026, heliocentric distance increasing 2 to 3 AU, brightness fading, magnitude 13 to 15. Professional instruments only. Tracking continues, astrometry refines orbit, ephemeris updates, future star passages calculated. Will 3 I Atlas approach another star? Gaia parallaxes, stellar positions, velocities, trajectory integrated, 10 million years forward. Statistical analysis, probable encounters, 1 parsec approaches, gravitational interactions, velocity changes, galactic orbit evolution, predictions uncertain, but calculable. Follow this object forever. Mathematically, legacy of 3. I Atlas, third interstellar object. Most chemically analyzed, most observationally documented, coordination unprecedented, Hubble, JWST, SphereX, VLT, GTC, Gemini, TESS, SWIFT, Mars spacecraft, Jupiter spacecraft, ground networks, amateur contributions, global effort, data archive permanent, future comparisons. When fourth interstellar visitor arrives, compare to 3 I Atlas, build statistics, understand interstellar population, size distribution, chemistry distribution, dynamic distribution, galactic origins, planet formation. Outcomes, exoplanetary system architectures, all constrained by interstellar visitors. 3. I Atlas cornerstone. Foundation laid, science continues. If you're following this journey, make sure you're subscribed because we're about to dig into what makes this object truly extraordinary. Comment below where you're watching from. This analysis relies on cutting-edge research from ESA's Mars Express and ExoMars Trace gas orbiter observation plans, published September 2025, plus NASA's multi-spacecraft coordination documented across Hubble, Webb, Mars Reconnaissance Orbiter, an 11 encounter spacecraft tracked in the August 21st paper by Lise and team on ARC-CIF 250.8.15768. Back to the data. Rotation period, significance deeper dive, 16.79 hours. Compare solar system comets. 67P Churyumov-Gerasimenko, 12.4 hours. 1P Halley, 2.2 days. 9P Temple 1, 41 hours. 1C Ison, 10 hours before fragmentation, wild variation. 3I Atlas middle ground, not unusually fast, not unusually slow. Typical comet rotation. Suggests normal formation, normal evolution, normal structure, until ejection. Then, billions of years unchanging. Rotation conserved, angular momentum locked. But 16 hours reveals more. Assume spherical nucleus 5 kilometers diameter. Calculate moment of inertia. Solid sphere. Moment equals 0.4, mass times radius squared. Rotation period gives angular velocity. 2 pi divided period. Angular momentum equals moment times angular velocity. For 33 billion ton mass, 5 kilometer radius, angular momentum 10 to the 18th kilogram meter squared per second. Enormous. Stabilizes rotation, resists perturbations. Interstellar journey preserves spin state. Consider ejection mechanism. Planet scattering implies torque. Close approach to Jupiter mass planet. Tidal forces. Differential gravity. Spin up possible or spin down. Depends. Geometry. Prograde encounter spins up. Retrograde slows down. Final rotation. Depends encounter velocity. Impact parameter. Planet mass. Complex dynamics. 3. I Atlas 16 hours. Models suggest moderate encounter. Not extreme, not gentle. Somewhere between. Alternative ejection. Stellar mass loss. Parent star evolves. Red giant phase. Envelope expands. Mass ejected. Gravitational binding weakens. Outer disk objects drift away. No violent encounter. No torque. Original rotation preserved. Formation spin rate, protoplanetary disk turbulence, eddies induce rotation, accretion adds angular momentum, collisions modify spin, final rotation reflects formation history, 16 hours perhaps, primordial, never changed, billions of years frozen. Non-gravitational acceleration, null result consequences. Upper limit 15 meters per day, squared. Translation, negligible trajectory change, 4.5 months observation. Position shift less than 0.028 arcseconds. At distance 2.6 AU from Earth. Physical shift less than 100 kilometers. Outgassing produces force. Mass loss 150 kilograms per second. Velocity 440 meters per second. Momentum flux 66,000 newtons. Continuous jet sunward side. Rocket effect obvious. Yet no acceleration. Mass too large. 33 billion tons minimum. Force divided by mass. Negligible acceleration. Math checks out, but implications stark. Traditional comet models. Nucleus mass. Few billion tons typical. 10 kilometers diameter. 2 Rotational, I Borisov, 0.5 kilometer diameter. Estimated mass 10 to the 12 kilograms, 1 billion tons. 3I Atlas, minimum 33 billion tons, factor 33 larger. Diameter scales as cube root, roughly triple diameter, 5 to 10 kilometers. But uncertainty huge, density unknown, porosity unknown. Ice to rock ratio unknown. Could be denser, smaller diameter, same mass, or less dense, larger diameter, same mass, high-rise observation. October 3rd, crucial, Mars Reconnaissance Orbiter, high-resolution imaging science. Experiment, 0.5 meter telescope. Resolution 30 kilometers per pixel at distance 29 million kilometers. 3 I-Atlas appears. Central pixel captures nucleus, coma transparent, brightness measured, albedo assumption applied, nucleus, size derived. 2 orders magnitude better than Hubble, uncertainty collapses. Diameter known, mass confirmed or revised. Answer days away. Population statistics. Problem? Interstellar object size distribution. Theory predicts power law. Small objects abundant, large objects rare. Exponent, -2 to -3. Differential distribution. For every 10 kilometer object, 1,001 kilometer objects, million 0.1 kilometer objects. Observational bias favors large. Brightness scales with area. Square of diameter, but detection threshold. Magnitude limit, distance factor. 3. I-Atlas discovered magnitude, 17. Oumuamua discovered magnitude, 20. Fainter limit means more small objects detectable, yet detection sequence wrong. First, Oumuamua, 100 meters estimated. Cigar or pancake shape, tiny. Second, Borisov, 500 meters diameter. Small comet. Third, 3I Atlas, 5 kilometers minimum. Giant, backward sequence. Should find 1,000 small before 1 large. Statistics violated, unless detection efficiency misunderstood, or population distribution flatter, or 3I Atlas outlier. Statistical fluke. Rare event. Probability low, but possible. Loeb emphasizes reservoir constraint, galactic rocky material budget, exoplanetary systems eject mass, planet formation efficiency, 10 to 50% disk mass into planets, remaining mass, dust, comets, asteroids, some ejected. Interstellar population, total mass finite, heavy elements limited, iron, silicon, magnesium, oxygen, carbon, all from stellar nucleosynthesis, galactic inventory constrained, too many large objects, budget exceeded, math doesn't work, unless formation efficiency higher. Or ejection mechanism selective, size-dependent ejection, preferentially large bodies. Giant planets scatter big objects easier, small objects remain bound. Possible bias, chemical composition revisited, Ko2 to water ratio 8:1, extreme value, compare comets. Typical ratio 0.1 to 1, factor 80 difference, only outlier, C 2016, R2 comparable. That comet showed pure CO2 emission, almost no water, spectral twin to 3, I Atlas, but C 2016 R2 solar system comet from Oort cloud. Ejected early solar system history, 4.6 billion years ago, formation zone beyond Neptune, cold environment, similar to 3 I Atlas parent disk, convergent chemistry, different stars, same physics, same ice line distances, same temperature regimes, carbon monoxide ratio. CO to water 1.4, closer to typical, not extreme. CO volatility high, Sublimits farther from sun than CO2. Activity begins early, expected, but ratio moderate, not dominant species. Carbon dioxide dominant, then CO, then water, inverted from solar system norm. Water usually dominant, then CO2, then CO. 3I Atlas flipped, reflection of formation, location, or radiation processing result. Cosmic rays convert water ice to CO2. Radiolysis, billions of years exposure, surface layer transformed, mantle enriched, CO2. Core still water rich. Stratification model, consistent observations, nickel without iron puzzle, industrial chemistry analog, nickel tetracarbonyl synthesis, Ni plus 4 CO yields NiCO4, Mond process, terrestrial nickel purification, temperature 150 Celsius, pressure 1 atmosphere, space conditions different, lower temperature, lower pressure, but carbon monoxide abundant, nickel metal dust, reaction feasible, product volatile, breaks apart, UV light, releases nickel atoms, observed emission, explains data, natural process, no intelligence required. Chemistry alone, but why no iron? FeCO5 exists. Iron pentacarbonyl, also volatile, should decompose, release iron atoms, not observed. VLT, upper limits, no Fe. One emission, abundance ratio puzzle, interstellar dust, nickel to iron ratio. Solar abundance, 1 to 18, iron dominant, nickel trace. Yet 3, I-Atlas. Nickel? Yes. Iron? No. Fractionation process. Selective chemistry? Nickel carbonyl forms. Iron carbonyl doesn't. Temperature dependent. Pressure dependent. Carbon monoxide partial pressure. Equilibrium constants. Nickel favored. Iron suppressed. Feasible. Models needed. Green glow mystery deepens. September 7th observation. Total lunar eclipse timing. 3. I-Atlas visible. Astrophotographers capture color. Green emission clear. Prior spectra. C2 not detected. C3 not detected. Carbon chains absent. Standard green emission mechanism unavailable. Alternative molecules. Cyanogen possible. CN emission. Green region detected by VLT. Could contribute, but typically weaker than C2. Insufficient for observed brightness. Unknown molecule. Organic fluorescence. Complex hydrocarbon. Aromatic compounds. Polycyclic aromatics. PAH emission. Possible green wavelengths. Unconfirmed. December observations. Critical. Earth distance 1.8 AU. Optimal geometry. Full phase. Maximum brightness. Spectroscopy. Feasible. High resolution. Echelle spectrographs. Identify emission lines. Wavelength precision. Molecular assignment. Green glow source revealed. Or new mystery. Unknown spectral signature. Unidentified emission. Chemical species. Never seen before. Interstellar organics. Complex molecules. Prebiotic chemistry. From another star. Analyzed first time. Water ice grain discovery significant. JWST absorption features. Fine grains. Sub-micrometer size. Amorphous structure. Not crystalline. Temperature signature. Formation below 100 Kelvin. Never warmed. Interstellar ice. Preserved from parent disk or formed in transit. Cosmic ray irradiation. Water molecules. Radiation damage. Amorphous state. Structure destroyed. Crystal lattice lost. Randomized arrangement. Lower density. Higher surface area. Sublimates easily. Explains extended sublimation. Beyond nucleus. 4 to 10,000 kilometers. Secondary source. Grains released. Drift outward. Solar heating. Delayed sublimation. Gas production continues. Far from nucleus. Carbonyl sulfide detection. OCS molecule. 0.43 kilograms per second. Trace component, but significant. Sulfur-bearing molecule. Pre-solar grain signature. Interstellar chemistry. Sulfur depletion problem. Where's the sulfur? Galactic sulfur budget. Unaccounted. Locked in molecules. OCS candidate. Frozen in comets. 3. I-Atlas contains it. Evidence accumulates. Sulfur reservoir. Cometary ices. Interstellar population. Galactic inventory. Sulfur located. Oxygen budget related. Galactic oxygen. Mostly TO. Some water. Some silicates. Oxygen and ices. 3. I-Atlas. Oxygen rich. CO2 dominant. CO present. Water present. Oxygen inventory high. Parent disk. Oxygen abundance. Solar or supersolar. Metallicity indicator. Stellar origin constrained. Not low metallicity star. Thin disk confirmed. Age younger. 1 to 5 billion years. Not ancient halo. Not thick disk. young stellar population, recent ejection, galactic timescales, temperature evolution modeling, heliocentric distance decreases, solar flux increases, surface temperature rises, sublimation rates increase, activity level grows, predictions, October perihelion. 1.4 AU, surface temperature minus 50 Celsius, CO2, sublimation vigorous, water sublimation begins, activity peak, brightness maximum, coma expands, tail lengthens, dust production increases, observations confirm or deny, real-time test, models validated or revised. Structural integrity question, no fragmentation observed through August, nucleus intact, cohesive strength sufficient, thermal stress tolerated, rotation stable, no tumbling, no splitting, contrast, Borisov, that comet fragmented, lost mass, nucleus weakened. 3. I Atlas robust. Composition difference, stronger matrix, rock fraction higher, binding better, or size advantage, larger nucleus, self-gravity dominates, holds together, mass sufficient, tidal forces negligible, stress limited, survives intact, spin state stability, 16 hours period, maintained through observation, no precession detected, no nutation, axis stable, moment of inertia, principal axis rotation, energy minimum, stable configuration, internal structure, homogeneous density, spherical shape, or elongated but stable orientation, tumbling absent, energy dissipation, internal friction, damp to minimum, rotation about maximum moment, physics requires it, cometary activity, sustainability, current rates, 150 kilograms per second total, 87% CO2, 9% CO, 4% water. Composition by mass, duration weeks, pre-perihelion, post-perihelion, months total, mass loss, integral, seconds times days times months, order 10 million kilograms, compared to nucleus mass, 33 billion kilograms minimum, fraction lost, 3 times 10 to the minus 4, 0.03%, negligible, activity sustainable, decades possible, centuries unlikely, but perihelion passage, weeks duration, easily sustained, no depletion risk, albedo implications, assumed 4%, typical comets, dirty ice, dark organics, carbon compounds, absorbing material, low reflectance, but interstellar exposure, cosmic ray irradiation, surface chemistry altered, albedo possibly higher, 10% feasible, icy mantles, bright surface, size calculation changes, diameter smaller, same brightness, or albedo lower, 2% possible, very dark surface, heavy organics, diameter larger, same brightness, factor 2, uncertainty, until high rise, direct measurement, albedo derived, uncertainty eliminated, phase curve needed, brightness versus phase angle, opposition surge, backscattering enhancement, shadow hiding, coherent backscatter, comet surface roughness, porosity indicator, regolith structure. 3 I Atlas observations, various geometries, phase angles changing, data collected, curve constructed, model fitted, surface properties derived, albedo refined, porosity estimated, texture inferred, dust grain properties, size distribution, submicron measured, water ice grains, dust component, silicates probably, organics certainly, carbonaceous material, size range, nanometers to micrometers, scattering efficiency, wavelength dependent, visible light, red color, large grains, me scattering, size comparable wavelength, infrared emission, thermal radiation, temperature dependent, dust temperature, tens Kelvin, far from sun, hundreds Kelvin, near sun, thermal models, size distributions, constrained, composition inferred, gas to dust ratio calculation pending, current data insufficient, gas mass rate measured, JWST, 150 kilograms per second, dust mass rate unknown, scattering brightness, coma photometry, model dependent, assumptions required, dust grain properties, size distribution, albedo, density, all uncertain, better data needed, direct measurement, infrared photometry, thermal emission, dust mass derived, ratio calculated, compared solar system comets, typical range 0.1 to 10, 3 I Atlas prediction, low ratio, gas dominant, CO2 rich, dust poor, speculation awaits confirmation, trajectory dynamics detailed, initial velocity vector, 58 kilometers per second, infinity velocity, hyperbolic excess, direction from Sagittarius, inbound angle, 5 degrees above ecliptic, nearly planar, convenient geometry. Planetary encounters enabled. Mars close, Jupiter close, not coincidence. Statistical probability. Ecliptic zone narrow, 5 degrees fraction of sky, 7%. Most interstellar objects. Random orientations, isotropic distribution, ecliptic passes rare. 3. Eye atlas lucky. Or not. Observers lucky. Access improved. Spacecraft opportunities, Mars missions, Jupiter missions, observation geometry optimal, scientific windfall, perihelion timing, fortunate, late October, Earth viewing, pre-conjunction, observations possible, post-conjunction, December access, viewing window, month's duration, maximum science, compare Oumuamua, discovered post-perihelion, already leaving, observations rushed, limited data, 3, iAtlas, discovered early, inbound leg, full coverage, pre-perihelion, during perihelion, post-perihelion, complete data set, activity evolution, full cycle, science maximized, Mars encounter significance, October 3rd, 28 million kilometers, Mars express ready, 15 years operational, experienced spacecraft, instruments calibrated, HRSC camera, stereo imaging, surface detail, if nucleus resolved, shape measured, rotation confirmed, omega spectrometer, infrared, 1 to 5 micrometers, molecular bands, CO2, water, organics, composition mapped, SPICAM spectrometer, ultraviolet, 200 to 600 nanometers, gas emissions. Dissociation products, O radicals, atomic oxygen, sodium possibly, exosphere probed, ExoMars, TGO edition, trace gas orbiter, nomad spectrometer, high resolution, trace species, methane sensitivity, isotope ratios, carbon isotopes, oxygen isotopes, deuterium to hydrogen, D to H ratio, water origin indicator, cometary water, solar system comparison, 3, iAtlas value, different star, different disk, D to H ratio, formation temperature signature, cold formation, high D to H, warm formation, low D to H, measurement, critical, origin constraint, astrobiological implications, Cassie's camera, color imaging, stereo capable, surface detail, context imaging, coma structure, jets, outbursts, rotation phase, sunlit hemisphere, shadowed side, contrast measurement, reflectance properties, spectral colors, redness measured, wavelength dependence, grain size indicator, composition clue, Jupiter encounter, distant future, March 16, 2026, 54 million kilometers, Juno spacecraft, polar orbiter, microwave radiometer, subsurface sounding, 3, iAtlas distance, marginal detection. Unlikely observations, but other spacecraft, Europa Clipper, launch 2024, Jupiter arrival 2030, gone by then, JUICE, Jupiter Icy Moons Explorer, ESA mission, launch 2023, Jupiter arrival 2031, also gone, Parker Solar Probe, Sun orbits, perihelion passes, 3, iAtlas. Trajectory, possible conjunction, solar distance, both near Sun. October 25, alignment possible, remote chance, legacy science, interstellar object number 3, most data, best characterization, chemical inventory, rotation period, mass estimate, size range, origin constraints, population statistics, model tests, theory development, follow-up studies, decades, refinement continues, archival data, preserved, future analysis, new techniques and better models, improved understanding. Comparative planetology expanded, solar system comets, Oort cloud, Kuiper belt, Jupiter family, long period, interstellar comets, 2, I-Borisov, 3, iAtlas, future visitors, population emerging, statistical sample, size distribution, chemistry distribution, origin distribution, planetary system outcomes, architecture diversity, formation models, tested, constrained, validated, exoplanet connection, giant planets, scattering efficiency, mass dependent, Jupiter analogs, eject comets, super-Jupiters, more efficient, sub-Jupiters, less efficient. 3, iAtlas ejector. Jupiter mass guess, 1 to 10 Jupiter masses. Parent system architecture. Multiple giants, likely. Scattering requires it. Mean motion resonances, dynamical instability, planet migration, disk dispersal, comets flung, interstellar space. 3, iAtlas result. SETI implications, Loeb hypothesis, technological origin, testable claims, October 3rd observation, high rise, nucleus size, under 5 kilometers, natural origin supported, over 5 kilometers, anomaly confirmed, December trajectory, Earth vicinity. November 21st to December 5th, intercept window, non-gravitational acceleration detected, maneuvering confirmed, hypothesis gains, no acceleration detected, natural origin prevails, science decides, data rules, speculation ends, but if natural, lesson learned. Interstellar population diverse. Chemistry varies, sizes vary, parent systems vary, formation zones vary, ejection mechanisms vary, galactic orbits vary, ages vary, every object unique. 3 iAtlas example. Future visitors, more diversity, more surprises, more science. Expect unexpected, universe creative. Physics allows, chemistry enables, life possibly, panspermia theory, comets deliver organics. 3 iAtlas organics, prebiotic molecules, if delivered Earth-like planet, around that distant star, life maybe, speculation reasonable, evidence insufficient, but possibility real. October 3rd approaches, high-rise images, nucleus revealed, brightness measured, 30 kilometers per pixel, nucleus spans pixels, or single pixel. Answer imminent, diameter derived, mass confirmed, models tested, anomaly resolved, or deepened. 33 billion tons, 5 kilometers, match expected, natural comet, slightly large, but reasonable. Over 10 kilometers, 50 billion tons, population statistics broken, theory revision, or paradigm shift, December 19th, Earth closest approach. Final observations, spectra, photometry, astrometry, color imaging, 3 months post-perihelion, activity evolution, compared pre-perihelion, symmetry tested, outbound equals inbound, or different, depletion occurred, surface layers removed, deeper material exposed, chemistry changed, fresh ices, pristine composition, or processed outer layers, mantle material, radiation cooked, dark organics, red coloration, March 2026, Jupiter region, final measurements, then farewell. Distance increasing, brightness fading, magnitude 15, 16, 17, detection threshold, lost to view, but orbit known, trajectory calculated, future path, galactic orbit, velocity vector, UVW components, change by Jupiter, new values, new direction, maybe towards some star, 10 million years, 20 million. Stellar encounter, possible. Probability calculable, but identity unknown. Galactic census incomplete. Gaia limitations, distance limits, faint stars, missed. 3. iAtlas departs, re-enters interstellar medium, cold darkness, cosmic ray bombardment, surface processing continues. Billions more years, until next encounter. Another star, another planetary system, maybe capture, maybe collision, maybe observation by other astronomers around that star, if they exist, if they watch, if they wondered like us. But one thing certain, October 3rd, 2025, high-rise targets. 3 iAtlas, central pixel glows, photons counted, 30 kilometer resolution, albedo correction applied, 4% assumption, may be wrong, but calculation proceeds, nucleus diameter computed, published within days, paper submitted, peer review, community debates, Loeb responds, consensus forms, or doesn't, science continues, truth emerges, data wins, always does. The brightness in that pixel will tell us if 33 billion tons of ice and rock simply drifted here from somewhere else. Or if we're looking at something that breaks every rule we thought we understood about interstellar debris, the number will either confirm the models or force us to rewrite everything we think we know about what gets ejected into the dark between stars.